Welcome to this explainer. Today, we're unpacking something incredibly fascinating, the anatomy of a lead engineer in the automotive industry. Specifically, we're diving deep into the highly technical role of a lead engineer for BIW closures and Upperbody. To really ground our exploration today, we're actually using a real-world position at Mahindra and Mahindra, specifically based at the Mahindra Research Valley in Chennai, as our anchor. We're going to focus intensely on the senior engineer's technical responsibilities because, frankly, the amount of skill and sheer problem-solving capability required for this role is just mind-blowing.
So here's our agenda for unpacking this technical tool belt today. We'll start by defining body in white, move on to designing metal and fittings, then mastering CATIA V5, exploring kinematics, basically making it move, and finally we'll wrap up with the complete engineering workflow.
All right, let's jump right into Section 1, defining body in white.
So the absolutely crucial point here is that before a car looks like that shiny, finished vehicle you see sitting in a showroom, it's just a complex, bare metal skeleton. And that raw skeleton is what the industry calls the body in white, or BIW. This entire stage happens way before any painting, before the engine is dropped in, and long before final assembly. As a senior engineer in this specific domain, you aren't dealing with leather seats or fancy infotainment screens. You're engineering the foundational metal architecture of the vehicle itself. Now, within that BIW skeleton, this particular job description specifically highlights closures. And when we talk about closures in this role, we're really looking at designing all the opening panels of the vehicle. This includes the doors, the hood or bonnet, the tailgate, liftgate, trunk lid, basically any opening body panel you can think of. These aren't just flat, simple pieces of metal, right? They're highly engineered structural components that literally have to protect passengers, look aesthetically perfect, and function flawlessly thousands and thousands of times over the lifespan of the vehicle.
Moving right along to Section 2, designing metal and fittings.
Now, what's really fascinating here is the stark contrast in expectations for a senior lead engineer. There is a massive difference between theoretical CAD modeling, which, let's be honest, is basically just drawing pretty geometry and shapes on a computer screen, and true manufacturing feasibility. The technical responsibility here isn't just making a cool 3D model, it's about deeply understanding sheet metal geometry in the real world. That means designing specific flanges, calculating exact bends, and adding the right reinforcements. The engineer has to ensure that the component they just designed can actually be stamped out of real metal, assembled on a factory floor, and used safely out on the highway. I mean, if it looks great on screen but can't be physically manufactured, well, it's straight back to the drawing board.
And it doesn't even stop at the large exterior panels. Beyond the doors and hoods, the senior engineer also has to design all the critical and often completely hidden fittings that hold the whole thing together. We're talking about cargo and body fittings here. These are your brackets, your mounting supports, heavy-duty reinforcements, and really complex fastening arrangements. These parts are absolutely essential to securely attach and support everything within the body and cargo areas.
Okay, let's get into the software side of things with Section 3, Mastering CATIA V5. This breakdown brilliantly illustrates how each specific module in the CATIA V5 software maps directly to a distinct and really vital engineering function. A lead engineer can't just know one little corner of the software, they have to master the whole shebang. You've got generative shape design, or GSD, which they use for creating and modifying those really complex automotive surfaces. Then there's solid modeling for the actual nuts and bolts engineering geometry. Once you have your parts, you use assembly design to put them all together and check clearances. After that comes FTA, functional tolerancing and annotation, which is totally critical for applying GD&T, or geometric dimensioning and tolerancing, making sure parts actually fit together in the real world. And finally, drafting, which translates that brilliant 3D model into 2D engineering drawings for the folks on the manufacturing floor. The company fully expects the senior engineer to own this entire 3D to 2D digital workflow.
Which brings us to Section 4, kinematics, making it move.
So here is a vital question for the lead engineer, and it represents a huge chunk of their technical responsibility. How do these complex, heavy metal parts actually move without colliding into each other? Just think about it for a second. Ensuring that a heavy car door can transition from fully closed to fully open smoothly without hitting the front fender or putting too much strain on the hinges, well, that requires incredibly precise mathematical and engineering foresight. And this is exactly where the study of closure kinematics comes in. The lead engineer has to study the entire path of motion. They are painstakingly checking the door movement, analyzing the hinge movement, verifying adequate opening angles, and hunting down any possible interferences or clearance issues with the adjacent components. Actually, scratch that. They aren't just checking it. They have to simulate the entire journey from the closed position right through the opening movement all the way to fully open, just to guarantee absolutely flawless functional operation. And to pull that off digitally, they have to manage some seriously complex joint data, using specialized digital tools like ABF or macro joint creation right inside CATIA. The engineer defines the exact mechanical relationship step by step. The digital model must perfectly map how the door connects to the hinge and then how that hinge connects to the main body. It's a literal 3-step digital handshake. And if this relationship is off by even a fraction of a millimeter on screen, the real-world kinematic simulation is just going to fail. Let's bring it all together now in Section 5, the complete engineering workflow. I absolutely love this point, because this quote perfectly captures the real essence of the lead title. The company essentially wants someone who can independently handle a BIW/closure design module. You know, it's not about being handed a blueprint and told to just trace it. Not at all. It's about complete independent ownership of the engineering module. It requires relying on deep, battle-tested engineering judgment. So when we say independent ownership, this is what it looks like in practice. The senior engineer is literally driving the entire problem-solving workflow. It's a 6-step journey. They start with a raw vehicle requirement, let's say a brand new door design. Step 1, they develop the concept. Step 2, they create the CATIA surfaces and solids. Step 3, they build the digital assembly. Step 4, they run those complex kinematic checks to make sure it moves right. Step 5, they apply all the GD&T and functional tolerances. And finally, Step 6, they create the 2D manufacturing drawings while at the same time resolving design issues and supporting the final release. They are steering the ship from a rough idea to a physical reality. Now, looking at this career hierarchy, you can immediately see why this is definitely not a junior position. You don't just walk out of college and do this. An engineer typically starts out as a design engineer, proves themselves to bump up to a senior design engineer, takes on way more scope as a module or project engineer, and only then reaches the pinnacle of lead engineer. It takes years of progressive automotive product development experience to build the kind of technical intuition necessary for this top tier. To put a number on it, mastering these technical responsibilities demands serious time. The Mahindra job posting specifically calls for 7 to 11 years of solid, relevant experience. Guys, that is nearly a decade of living and breathing sheet metal, CATIA V5, kinematics, and manufacturing feasibility to even be considered for this level of responsibility. So this explainer leaves us with a final, somewhat provocative thought. Mastering BIW engineering at a senior level isn't just about memorizing which buttons to click in your CAD software. It is entirely about having the hard-earned, independent engineering judgment to drive a concept from a raw requirement into a fully manufactured physical reality, one that ultimately keeps people safe out on the highway. So ask yourself, do you have that kind of judgment? I really hope this deep dive into the anatomy of a lead engineer gave you a brand new appreciation for the incredible technical minds building the cars we drive every single day. Keep learning, and we'll catch you on the next explainer.